Hey everybody, Sakani here. So we see we have this diagram over here. I'm guessing it's going to do something with maybe potential energy or like maybe time period, something to do with springs, right? So let's actually read the question right over here. A student conducts an investigation to determine the relationship between period of oscillation, of a system consisting of a block and n attached springs. So we don't know how many springs there are just n attached springs. The student starts with a block of mass m attached to a single ideal spring of spring constant k, as shown in figure 1 over here. The student holds the block so that the spring is neither stretched nor compressed at a vertical height of 1 meter above the motion sensor. The student releases the block from rest, and records the period of oscillation for the system consisting of the single spring and block. Additional identical spring is attached in parallel, as shown in figure 2. So here there was just one spring and now here are two springs in parallel. And the procedure is repeated for n equals 2 springs. The procedure was essentially just releasing the block from rest and then recording the period of oscillation. The procedure is repeated through n is equal to 10 springs. And then let's just dive right into part A. So part A is derive an expression for t, and we know t is the time period, as a function of n. Express your answer in terms of m, k, n, and physical constants as appropriate. So right off the bat, I know we're talking about time period, right? So I'm assuming that I need an equation for the time period of a spring. So now I'm going to try and find the equation for the time period of a spring because maybe I just don't remember it at the top of my head. So I see that, over here it says t is the period, which is exactly what I want. So I'm going to find t. I see that there's one t over here, but that has to do with some angular stuff. And I don't think that question is asking us anything angular related. So we're going to skip over that. I see that this is the equation we want because it has that exact subscript I want, s, which is spring. So I see time period of a spring is equal to 2 pi square root m over k. So let's actually hop on back to part A and use this equation. All right, we're back at part A and I'm going to write that equation I just saw. So t is equal to 2 pi square root m over k. But let's go back to the question. It says to derive an expression for t as a function of n. Over here, we don't have n, so we need to find a way to get n into that function. But other than that, we do have m, which is correct, and we do have k. We just need a n. So in order to find an n, this is what I'm going to do. I know that n is the number of springs you attach to that mass, right? And that goes from n is equal to 1 all the way to n is equal to 10. So as we increase the number of springs, the spring constant of the system, I would say, is going to change as well. So I know the equivalent spring constant is going to depend on how many springs I have. So if I consider just one spring, the spring constant of the whole entire scenario is going to be k. If I consider 2 springs, what is the spring constant of the whole entire scenario? So essentially what I'm thinking is that I know in this case I have 2 springs, right? If I just want to create a system where it's just one spring, what is that spring constant going to be? So in order to do that, we need to figure out one really important thing in the question, and that says parallel. So whenever we're talking about parallel, that means that all these springs are going to be in parallel. So in this case, it's a horizontal line. And whenever we have springs in parallel, let's say we have k, 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 which is a spring constant. The spring constant as a whole of the scenario is just going to be 4k in this case. You're just going to add those spring constants. So for one spring, the total spring constant of the scenario was k. For 2 springs, the total spring constant of the scenario is 2k. And then hence for 3 springs, it's going to be 3k. And then for 10 springs, it's going to be 10k. But we want it in terms of n, right? So for n springs, what's it going to be? Yeah, it's going to be nk because it's just k plus k plus k n times, so just nk. So now we can actually replace this k, which is the spring constant of the entire scenario, with our nk. So it's going to be t is equal to 2 pi square root m, and then k we're going to replace for nk. And that is going to be our final answer. All right, now on to the second problem. It says on the following axes, sketch a graph of t as a function of n for when n is greater than or equal to 1. Okay, so let's go back to the top where we saw our function, which was t is equal to 2 pi square root m over nk. And now they're saying just sketch a graph of t as a function of n, right? So this is what I'm going to do. Whenever I see a problem like this, I like to just replace in numbers. So I know the mass, it's going to just stay constant, right? So I'm going to say the mass is, I don't know, maybe like 20. So my new function is going to be t is equal to 2 pi square root of 20 over nk. Now I can also give a value for k, right? Because I'm giving values for every variable that's not changing. Because I see that in this problem, we're just comparing t and n, so I can't replace values for those. I can replace values for everything else. So I can replace values for k as well. So t is equal to 2 pi square root 20 over, I don't know, 0.7 n. So here k was equal to 0.7, right? And now I'm just going to graph it on my calculator. So as you guys can see over here with the graphing calculator, I see it has some sort of this type of curve. So I'm just going to draw it over here on our graph. So I'm just going to draw something like that, okay? And no need to label anything else. It's just, they just want to see the curve, right? So that's pretty much it for part B. Let's move on to the part C. All right, so part C says the student plots the data for t squared as a function of n to the power of minus 1 as shown. So this is basically 1 over n, right? Okay, so this is the graph. And part C and then part 1 says draw the best fit line for the data. Okay, that's not too bad. I'm going to attempt to draw a best fit line of the data. So let's do something like that. All right, so that's our best fit line. And just like that, we're done with this part. All right, now we have the mass of block measured to be m is equal to 1.5 kg. Okay, that's good. They give us some number. Using the graph, calculate the experimental value for the spring constant k for a single spring. So now we have to calculate the spring constant of one spring. And one thing to note is that they say for a single spring. That is the same thing as saying n is equal to 1. In order to find the spring constant, I'm going to go back to my previous equation of the time period. And that equation was just t is equal to 2 pi square root m over kn. Now, before I start substituting numbers in, because I know that is a common misconception, because I know they gave you the mass and we know the value of n, so why don't we just substitute those in this equation? But if you realize really closely that this looks a little bit similar to what we see on this graph. I know the y-axis is t squared and the x-axis is 1 over n. And that is kind of like what we see in this equation. I mean, we could square both sides to get the t squared. And then I see that we have n in the denominator. So I'm going to try and focus on this equation instead of just substituting numbers in. So first, I want to get that t squared. So I'm just going to square both sides, squared, and then m over kn. And now I think I'm ready to substitute that m back in. So I'm going to have t squared is equal to 4 pi squared 1.5 over kn, right? Over kn. And they're asking for a spring constant. So I'm going to take k to just one side because that's what we're trying to find out. So 4 pi squared 1.5 over t squared n. One thing I want to note is that this is basically rewritten as 1 over n, right? Because n is in the denominator. I could rewrite that as n to the power of minus 1. So I'm going to rewrite this. Whoops, I'm going to rewrite that as k is equal to 4 pi squared over 1.5 over t squared and then n to the power of minus 1. The reason I did that is, once again, the x-axis is n to the power of minus 1. And I could see from over here, I'm going to focus on this part. This is n to the power of minus 1 over t squared. And the slope over here is t squared over n minus 1. In other words, t squared n, right? But let's just focus on t squared over n minus 1. So from here, let's actually try to find the slope first, because once I find that slope, I can just take the inverse of that slope and plug it back over here. So let's find the slope of this. I'm just going to take 2 points. I am going to take this point over here and this point over here. All right, so I found the slope as 12.33 with the help of my calculator. And now I know that the slope is 12.33. In other words, t squared over n minus 1 is 12.33. But in our equation, I see that we need n to the power of minus 1 over t squared. So basically the opposite of this. Well, no problem. We could just take the inverse of this. So that would be 1 over 12.33. And then that, with the help of my calculator, is equal to 0.081. So now let's replace this by 0.081 that we just found. So we get 4 pi squared over 1.5, 0.081. And solving that with the help of my calculator, that is equal to 4.8. And that is our final answer. All right, so on to the third part, we see that the student finds that the value given by the manufacturer for the spring constant is larger than the value determined experimentally. So in other words, the actual value is greater than what we calculated. And what we calculated was that 4.8, right? Determine a single source of experimental error that could result in the observed difference 4K. Briefly justify your answer. Okay, so of course there could be a lot of error. There could be like air resistance, maybe the mass wasn't calculated properly, but I want to dive a bit deeper into that because they say a really important thing in the first line. They say that the actual value of K was greater than what we calculated as a value of K. So once again, I'm going to go back to this equation, of course. So I'm going to just rewrite it. 2 is equal to 2 pi square root m over kn. And over here, what I realize is that t is inversely proportional to square root of n. In other words, if n increases, then time period will decrease. I also notice that t is inversely proportional to square root of k. I see that as n increases, the time period will decrease, right? The time period will decrease. And if the time period decreases, then as seen over here, the spring constant will increase. All right, so the spring constant has increased, right? So what we could say is that maybe the time period was calculated wrong. Maybe we said that the time period was much more than what it actually was, because if we say the time period is more, then that means we're going to say that the spring constant was less, right? Because they're inversely proportional. So if we calculated a greater time period than the... So essentially what I wrote is that if we calculated a greater time period, so if t increases, then the k value would decrease, which is why what we calculated was so much less than the actual value. All right, so this is our last part. Part D, the student conducts a similar investigation to determine the relationship between the period of oscillation of the system consisting of a block and the number n of identical spring, but arranges the block spring system horizontally on the table as shown in figure 3. So earlier it was like vertical, now it's horizontal. Frictional forces between the table and the block are negligible. In each trial, the block is displaced the same horizontal distance from the equilibrium and is released from rest. So part 1, the student plots t squared as a function of n to the power of n minus 1 for this new data, which is the same graph we just looked at. Would the slope of the best fit line from this new investigation be greater than, less than, or the same as the slope of the best fit line in the previous part? And then we have to justify our answer. So the slope of that best fit line was t squared over n to the power minus 1, or in other words, t squared n. But let's actually find the value of t. I know that t is equal to 2 pi over square root m k, and I know that these springs are in parallel, right? So this k is once again going to become kn if we have those n springs. And I think that's pretty much it, because this looks exactly the same as the previous equation we got. So the previous scenario, even though it was vertical and like gravity was acting upon it, the time period isn't affected by the gravitational force. It's just affected by the mass, which is the same in both cases, and affected by the spring constant, which is also the same in both cases. And of course, n, the number of springs you have. So I honestly think that it's going to be the exact same. And my reasoning for this is, I'm just going to explain it, I'm not going to write it, but my reasoning for this is that the time period only depends upon the mass and the spring constant, both of which are the same in the previous part and this part. So the time period is exactly the same. As for the slope, which is t squared over n minus 1, or just t squared n, I know that t squared is the same, right? Because we said t was the same, and n is also going to be the same because it's just the number of springs. So because everything is the same, just the orientation is different, but the orientation doesn't really matter in terms of t or the slope. All right, so our last part for this problem is when n is equal to 1, the maximum speed of the block is found to be Vmax, okay? When n increases, so when the number of springs increase, will Vmax increase, decrease, or stay the same? And then we have to justify our answer. Okay, so whenever I see something like maximum speed, I always think back to conservation of energy, because I know we're going to have kinetic energy for sure, because it's dealing with velocity. And I know there's also going to be spring potential energy, because we're dealing with springs. So in our problem, it said that it's going to start from rest, correct? So that means there's no kinetic energy at first. So I'm actually going to write KE plus PE is equal to KE final plus PE final. So initial kinetic energy is 0 because it starts from rest. Spring potential energy is going to be 1/2 kx squared. I'm just writing the general formula, not substituting any values right now. And I know that the final kinetic energy is going to be 1/2 mv squared. And then final potential energy is going to be 0 because we know that when the block has achieved maximum speed, then potential energy is going to be 0 because all that potential energy would have converted to kinetic energy already. So our equation is just going to be this equation right over here. And now we have to see, will Vmax increase, decrease, or stay the same? So I'm trying to find a relationship between velocity and n. But over here, I don't have n, so I need to figure out a way to get that n into that function. So I'm first going to simplify this. I know that v is equal to kx squared over m, all right? And now I need to find a way to get n into this problem. So in order to get n into this problem, I know that this k, of course, it has to be k of the whole entire system. So v is going to be equal to that same exact thing, nk x squared, excuse me, over m. So now I'm going to simplify this a little bit. V is equal to x square root nk over m. And here I see that velocity is directly proportional to the square root of n, meaning that if n increases, then velocity will also increase. So I am going to say that velocity will definitely increase if n increases.